In this video, we are going to talk about how molecules interact with each other and describe the way they interact. And then we're going to rank those interactions. And then we're going to predict and explain melting and boiling points. Okay, so the first thing I want you to do is draw the Lewis structure of water, H2O. It has 6 valence electrons. Hydrogen has 1 times 2. That's what water looks like. Now, let's label the water molecule with its electric dipole. Where is my partial minus? Where is my partial plus? Where is my magnet in this molecule? So I have my hydrogen's less electronegative. That gives me my partial plus. My oxygen's more electronegative. Oops, that's not red. The oxygen's more electronegative. That's going to be my partial minus. Do a figure eight on 8, but just stop, boop, short. I don't want to finish it up. I'm going to stop on the top and partial minus because it's the more electronegative one. So this is my electric dipole. I have my partial plus and my minus. And it says label the water molecule. Okay, I did that. I gave it its plus and its minus. Now considers what happens when two waters approach like this. So before we do that, I want you to think about what would happen if I brought a magnet. It's a weird shaped magnet, circular, but I have a magnet, and I tried to bring two blue things together like this. You'd say they're going to repel each other. They're going to repel each other, right? Well, guess what? The same thing happens if water comes in like this and another water comes in like this. And because that bond is polar and it's created that electric dipole, it has polarity associated with it. I have this hydrogen here and that hydrogen here are approaching each other. And they're going to repel each other. They're going to repel each other. They're going to want to go the opposite direction because this has a partial plus and that has a partial plus. Because oxygen is so electronegative, it's pulling the electron density from that hydrogen, giving this a plus. So that would be they'd repel each other, repulsion. And repulsion, you'd say higher in energy. They're not going to want to do that because we know systems go towards more stable things, lower in energy. So how would this look? It can look a lot of ways in 3D. I'm just going to pick one. So I know my oxygen is my partial minus. I have my partial minus. And this hydrogen has a partial plus. And I'm going to bring in another molecule. Well, I'll make this one, this hydrogen, I'm gonna make this hydrogen blue because I didn't have space for it. So that hydrogen, it also has a partial plus, boop, because of that polar bond. And now they're attracted to each other. So those two things are attracted to each other. Those two water molecules are attracted to each other. And the way we like to show this is we'll put a little dot, 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 because we don't want it to look like a bond. I don't want it to look like a lone pair either. I want it to be very obvious that those two are just attracted to each other, okay? They're seeing each other across the room, getting close, boop, 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 dot, dot, dot. That, the way we show dot, 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 that's the way we show the attractive interaction. They're attracted to each other. So the repulsion would be this guy, higher in energy. These two are like, ooh, let's get close. There's an attraction, and that would make it more stable. Okay. So when we have attractions between molecules, we have not talked about this yet. Finally, we're talking about molecules interacting between each other. They're interacting. They are called inter means between molecules, molecular, between molecules forces. Remember, those are attractive forces or repulsive forces. They either want to come closer to each other or be farther away from each other. That's what a force is. So intermolecular forces, it's a very large word for just saying attractions between molecules are called between two molecular forces. They are not bonds. They're not bonds. They're not bonds. They're not bonds. They're attractive interactions. So if I have an ionic bond or a covalent bond, they're sharing them. Those are real bonds. We call those bonds. They're very strong. Oops. So if I have my pen's going wacky. If I had, say, hydrogen and hydrogen, that covalent bond, they're sharing those electrons evenly. These are very strong bonds. Intermolecular forces are not as strong as that, but they're attracted to each other, and they're going to dictate things like melting point, boiling point, solubility, all kinds of cool things. Okay, so I told you that these intermolecular forces, like, they are not bonds, shouting at the universe. And then I flip it over and it says hydrogen bond with air quotes. Okay, so what I just showed you, that water being attracted to another water, they're attracted to each other. This attraction right here is actually called a hydrogen bond. The worst misnomer in the world. Nothing I can do about it. It's been called that forever, and it's the name for an intermolecular force. It is not a bond, but we call it a hydrogen bond. It's out of my pay grade. Nothing I can do about it. Hydrogen bond is not a bond. It's a very strong attraction between hydrogen on one molecule and a lone pair on another. Now, for us to have specifically a hydrogen bond, for me to have this attraction, the hydrogen has to be attached to the very electronegative. If you look at your periodic table, you have F and O and N. It's going to be attached to these atoms, N, O, or F. So hydrogen will be attached to those. So I can have a hydrogen bond with an NH, I can have a hydrogen bond with an OH, or I can have a hydrogen bond with an FH. Any of those will work. And that's because they're very polar covalent bonds. Why are these very polar covalent bonds? Why are they very polar covalent? Electronegativity differences. The ability to pull electrons towards themselves in that bond. Instead of sharing them equally, fluorine's a hog. It's going to pull them. So because we have these electronegativity differences, we have very polar bonds. The very polar bonds give us a, we could call it a permanent dipole, all because of electronegativity. The hydrogen atoms has a very partial plus, a very large partial plus, right? Because those electrons in that bond are going closer to the oxygen, leaving hydrogen with less electrons between them. So I need these things. And this little picture doesn't show you, but this is a lone pair on oxygen. That lone pair is the thing that's associating with that hydrogen. Okay, so that's what a hydrogen bond is. Air quotes on the bond. That's not really a bond. I won't always include the air quotes, but I will for a little bit just to remind you. Eventually, I'm going to take those away because in real life, they're taken away. It's not a bond. Okay, so here we have, it says label the dipole. So periodic table, CNOF, BCNOF, H pops in right above it. And we know as we go here, this is most electronegative, and the thing farthest to the right will have a partial minus. So I have a hydrogen attached to a nitrogen. Nitrogen is more electronegative than hydrogen. So I could put all of these as blue. All of these is blue. Nitrogen's the more electronegative atom. It's hogging the electron density in these bonds. It's saying, hey, the electrons are going to be closer to me. And the result is I get a partial minus here. And I get a partial plus here. This is my little mini magnet. This is my little mini magnet. This is interacting now. It's a very strong attraction. Ooh la la. Ooh la la. Very strong attraction. And we call this a hydrogen bond. Oh, you can tell it's late. I'm doing ooh la la in the video, and I'm definitely not going to remake this video unless I make a big mistake. Okay. So that is our first one. We are showing the hydrogen bond between those. A hydrogen bond is our first intermolecular force. It is the strongest intermolecular forces that we're going to see when we have only covalent bonds. Okay, so let's look at our second one. This is just a recap. We'll come back to this. I just say very polar bonds, a permanent dipole because I have the superpolar bond. It's the strongest attraction, and here are a couple of examples. So we're going to come back to this. We'll come back to this because you haven't learned it yet. So we know classifying polar bonds as nonpolar. I already talked you through this. We already know that basically we're always going to classify them between two nonmetals as polar unless we have a CC or a CH. However, I also categorize in my head hydrogen's just this tiny little guy. And when he's with these very electronegative atoms, it's a very special bond that's able to hydrogen bond. So I put these in a separate spot in my head. Yes, they're very polar bonds. And because hydrogen's so small and partial plus, it's going to hydrogen bond. Now I still have all these other polar bonds and they're going to behave in the same way. They're still going to have a permanent dipole. I'm still going to have differences in electronegativity that I can assign, and the molecules are going to interact in a similar fashion. So let's look at it. We have dipole-dipole forces are another type of intermolecular force that occur between molecules with polar bonds. Polar, covalent, understood that it's covalent, polar covalent bonds. They have permanent dipoles that give me a partial plus and give me a partial minus. An example, carbon to oxygen, carbon to nitrogen, and carbon to fluorine. If I drew my little periodic table, CNOF, CNOF, the difference between all of these is enough. Carbon to nitrogen, carbon to oxygen, carbon to fluorine, all of these are polar bonds. So an example would be HCl. So let's do HCl. You say, ooh, it's between two nonmetals and it's not the CH, so I know it's definitely a polar bond. Cl's right here below fluorine. Chlorine is more electronegative than hydrogen. So I have HCl. This one, maybe I'd need to give it to you that chlorine's more electronegative, but pretty much when you're over on the right side of the periodic table, it ends up being more electronegative than carbon. But I don't think it wouldn't kill me to give you those values just so you don't have to guess. So hydrogen versus chlorine. Chlorine's more electronegative. Oops. Chlorine's more electronegative. Let's keep it minus with the red. Hydrogen is less electronegative. The less electronegative gets the partial plus. The more electronegative gets the partial minus. And here we have a little magnet, little dipole. I have a dipole between HCl. Another HCl can come in and the same thing will happen. They'll line up, interacting with each other, attracted to each other, and we call this a dipole. So this is called a dipole, right? We have a dipole and dipole, a dipole, dipole. They're interacting because I have a dipole-dipole. A hydrogen bond, that is a dipole-dipole too, but it's such a special one that we have a special name for it. I have my partial plus and partial minus. I have my partial plus and partial minus, and I could continue on drawing these, and they would be attracted to each other. They'd be attracted to each other, just lining on up. I want to point out that maybe you would have drawn this differently. Maybe you would have said, maybe you picture, let's zoom in on this guy. Maybe you put your hydrogen over here and a Cl over here. That would absolutely be okay. I don't know, maybe it does both, probably does both. I don't really know. So don't worry about those tiny little details of where exactly am I going to put it in space. Just recognizing that you have this because of the polar bond that's present. It has a permanent dipole, really has a plus and a minus, and those are going to interact And when they interact, it's called a dipole-dipole. Pulling them apart is going to take some energy. They're attracted to each other. It's not a covalent bond. I always picture a covalent bond being like, we have a rope between this that's super glued onto our hand or something. Like really, really, it's hard to break. Dipole-dipoles, maybe we're holding hands and then you just let go. We're attracted to each other. There's an attraction, but it's just an attraction. It's not a bond. So this is just recapping what I said. And we note, so this is an important concept that you need to know. Put on your 4x6 card if you need to. Dipole-dipole are weaker than hydrogen bonds. Hydrogen bonds are strong. They're very strong. Picture being a very strong magnet. These, yes, I have a magnet, but it's not as strong. So it's easier for me to pull those apart. Okay, I think we're good for that. I'm going to stop and see you in the next video for dispersion forces.